Look at this estimation jar. If you had to guess the average length of the items inside, the mismatched keys, crayons, and puzzle pieces make it difficult to find a single reliable number. Scale that problem up to an industrial level. In modern manufacturing, massive data sets of raw parts are rarely neat or symmetrical. We call this raw data the parent population. It's often heavily skewed. The data might show exponential decay, where most parts fail early. It might be uniform, presenting as a flat, unpredictable box. Or it could be parabolic, clustered entirely at extreme highs and lows. We need a point estimate, a single numerical value to represent the true center of that population. But when the raw data is this erratic, finding one reliable number seems mathematically impossible. Determining the effective life of a component inside a jet turbine engine requires a degree of precision that pilots and passengers depend on. Engineers face a physical limitation. They cannot afford the time or the cost to test every single manufactured turbine component until it breaks. If they test only a small handful of engines and the parent population's lifespans are skewed, they might pull extreme outliers. This yields an inaccurate point estimate that misses the true average. Without a method to filter out the underlying noise of the parent population, quality engineering would rely on guesswork rather than science. To find the signal in that noise, statisticians stop looking at individual components. Instead, they pull small groups of parts, average them together, and plot those averages. This creates a sampling distribution, a separate statistical population made strictly out of those sample means. This is where the Central Limit Theorem takes over. It states that as the number of observations in your sample increases, the shape of this new distribution automatically approaches a normal distribution, the classic bell curve. This chart proves the theorem by starting with the U-shaped parabolic parent population. When we take samples of 2, the extreme edges collapse inward. At a sample size of 5, a distinct peak forms. By size 30, the original skew is overwhelmed, smoothing into a symmetrical bell curve. This histogram visualizes how those individual sample means, labeled as X bar, physically stack up. The exact center of this population of averages is perfectly equal to the true mean of that original chaotic parent population. But the data doesn't just form a bell. As the sample size grows, the entire distribution actively compresses inward. The mechanism driving this is called standard error. By dividing the standard deviation by the square root of the sample size, the math physically squeezes the variation out of the curve as your samples get larger. This tighter curve minimizes the distance between our sample mean and the actual population mean we are trying to estimate. The Central Limit Theorem collapses uncertainty into a measurable target. Quality engineers use this theorem as a lens to analyze overlapping production lines. Six Sigma black belts use it to calculate the difference in means between an old manufacturing standard and a newly improved one. This spreadsheet shows the math in action. Because the sample size is sufficiently large, engineers can calculate z-scores and determine probabilities, like this 98.4% result, without needing the individual components to behave normally. By bypassing the noise of raw data, this blueprint allows industries to guarantee product safety and scale operations with a quantifiable margin of error. This theorem functions as a primary tool for understanding any system where individual outcomes seem random. A single engine failure or a single data point tells us very little about the health of a manufacturing process. But by aggregating those samples and measuring the standard error, we can identify a stable, predictable center within any sufficiently large collection of data.